present some. Today I'm going to present some of our recent works on representing mixed integer linear programs by graph neural networks. Yeah, so this talk is based on some joint works with Jialin, Xiaohan, Xingshang, Jianfeng, and Wotao. This is the outline of the presentation. So I will first introduce MILPs and some preliminaries. Then I will talk about some known results about the subtraining power of graph neural networks. Then the last three sections will be about the approximation theory of graph neural networks for representing linear programs and mixed integer linear programs. So, let me first define the general form of mixed integer linear programs. So this is a general mixed integer linear programs, which is a constraint optimization problems, and the objective function is a linear function. The c is the coefficient and x is a variable, and the constraint is also linear. So ax circle b, where circle is a collection of smaller than or equal to or greater than or equal to. Then we have some lower bound and upper bound of the variable x, and some entries of x are constrained as integers. So where where I is a subset of 1 to n, then if j is in the subset of I, then xj is constrained as an integer. So if the subset I is an empty set, then we say that there's no integer constraints, and the problem is linear programs. So here is an example of MILP. So we can say, okay, the objective function is linear, and we have several linear constraints, and we have some upper bound. And here we don't have lower bound, which means that the lower bound is negative infinity, and x2 is constrained as an integer. But here are some basic concepts of MILPs and LPs. So we see that our problem is feasible if there exists some x that satisfy all the solutions, that satisfy all the constraints, and such x is called a feasible solution. And we see that the problem is bounded if it is feasible, and the objective value can be arbitrarily good, which means that for any r greater than epsilon, the objective function can smaller than negative r. And we see that x star is our optimal solution if it is feasible, and the objective value of x star is better than or equal to the objective value for any feasible x. And let me mention that it is possible that a problem admits multiple optimal solutions, but an interesting fact is that for an LP problems without integer constraints, then it is, and if we assume that it is feasible and bounded, then the optimal solution with the smallest L2 now must be unique, even if that it may admit multiple optimal solutions. So then let me introduce the MILP graphs. That the idea is first from the paper by Gassi et al. In 2019. So they propose that we can model MILP problems as a bipartite graph, and then we can apply some graph neural network techniques to learn the properties of LPs and MILPs. So first, it is a bipartite graph, and the first group of nodes is the first group of nodes represents the constraint, and the second group of nodes represents the variables. So vi corresponds to the ith constraint, and it is assigned with some features. So here, for example, v1 corresponds to the first constraint, and we collect all the features. So we collect all the information in the first constraint, so greater than or equal to 1. So we collect those information and put them as the feature of v1. And similar, we do something for v2. Also for w1 and w2, w1 corresponds to the first variable x, and we also assign some features for x1. The features consist of the coefficients of x1 in the objective function. Also, the lower bound of x1. So here x1 has no lower bound, so the lower bound is negative infinity. Also the upper bound and whether x1 is an integer or not. 0 means x1 is not an integer variable. So here, however, for x2 we have the last entry of the feature is 1, which means that x2 must be an integer. Also, this is a bipartite graph, so we need to assign the weights, the weights of the edge connecting the node Vi and Wj. So the weights of the edge connecting Vi and Wj is the coefficients of xj in the ith variable. For example, we can say, okay, so the coefficients of x2 in the first constraint is 3. So this edge is assigned with 3, and we assign the weights for all other edges. So that's the MILP graph. And with the problems modeled as a graph, we can use some graph neural networks to learn the properties of those problems. So where I think the most efficient or the most natural idea is a so-called message passing graph neural networks. So, well, the initial so in the initial layer or the layer L equal to 0, so we do some embedding. So where P0 and Q0 are the embedding corresponding to the nodes V and the nodes W respectively. So we first use P0 and Q0 to embed the features into some vectors. Then we do the message passing layer. In the message passing layer, so the features of each node are updated using its feature in the last layer and all the features from its neighborhood. So for example, if we want to know the feature of SI in the else layer, we use its feature in the L-1 layer, and we use all the features of the nodes in the other group, the features of TJ, then we update the feature. So we do a local update for the feature of TJ, then we do a message passing, means that, okay, so we convey the information, so or we transfer the information from TJ to SI. This message passing process is a linear combination with the linear coefficients being the weights of the edge. Basically, the message passing layer consists of 2 steps. So first step is the local update, then the second step is the message passing. So the information is passed to the neighbors. Then we do another local updates to get the feature in the else layer. And finally, the last layer has two different types. So we have the graph level output and the node level output. The graph level output means that we output a single scalar for the whole graph. So we take the average of all the features in the last layer, then we have an output function to output a single scalar, which is the property of the whole graph. And the node level output is that we output a vector, and with each entry being with the jth entry being the output corresponding to the Wj. So we take the average and we use the feature as Wj, then we have an output function, we output a scalar. So we compute a scalar, which is the output of the jth nodes, and the whole vector is the output of the whole graph. So, and one question is that why we want to use graph neural network to predict or to learn the properties of LPs and MILPs. I think the answer is that the graph neural network is permutation invariant, or it is permutation equivariant. So suppose that we have a MILP problem and we want to learn whether it is feasible or not. So if we permute all the variables, then we do not change the feasibility. Right? So if one problem is feasible, then after permuting all the nodes, then it is still feasible. So we should have some neural network structure that is invariant under the permutation. And the graph neural network, by the construction, is permutation invariant. So if we permute all the constraints and we permute all the variables, then the output does not change. Means that okay, one a feasible problem is still feasible. Also, the graph neural network with node level output is equivariant. Means that if we permute all the variables, then the output is permuted accordingly. So if we permute, if we switch x1 and x2, then the optimal solution is can also be changed by switching the first and the second entries. So that's one advantage of graph neural network and why it is suitable for solving LPs and MILPs. Now I'm going to present some results of the separation power of graph neural networks. So first, graph neural network is not perfect. So I use MPGN to denote the message passing graph neural network. Suppose we have those two graphs. So obviously they are not isomorphic. They are not isomorphic because the topology of those graphs are different. So the first graph is connected and the second graph is not connected. However, if we input these two different graphs into a graph neural network, then we'll have the same output because so recall that the MP graph neural network is constructed by the message passing layers, and we can say even if these two graphs are different. So if we take a look at the blue nodes, so each blue node has two neighbors that are red, right? So V2 has two neighbors, two red neighbors in this graph, and V2 also has two red neighbors in this graph. So if we only use the information from the neighborhood, so even if these two graphs are different, we can see the node V2 from both graphs, they will have the same neighborhood information. That's why, so if we input these two graphs into a graph neural network, that we will have the same output. So, which means that the MP graph neural networks cannot predict, cannot have different output for these two non-isomorphic graphs. That's a fundamental limitation of graph neural network. So this property is first proved in the paper by Xu et al. They proved that MP GNNs will have the same separation power as the so-called WL test, which is a classical algorithm for the graph isomorphism problems. So if we input these two graphs into WL test, the algorithm will identify them as isomorphic, but in fact, this is a wrong claim because they are not isomorphic. And let me put the pseudocodes of the WL test here. So WL test is constructed the iteration of WL test is very similar to the iteration of graph neural networks. So instead, the local updates are replaced by the hash function. So it only identifies whether the features are the same or not if hash function is injected. So let me summarize the separation power of graph neural network here. So suppose that we have two graphs, so two LP graphs or two MILP graphs, G and G hat. So if they can, then the followings are equivalent. So they cannot be distinguished by WL test if and only if they can. So for any GNF with graph level output, they will have the same output on these two graphs. And also, this is equivalent to the fact that if we have any node level output, then if we have any graph neural network with node level output, then the output on G and G hat will be matched by a permutation on W. This theorem can be proved by a famous theorem in functional analysis called the Stone-Weierstrass theorem. So the Stone-Weierstrass theorem says that suppose that we have some compact and Hausdorff space, and we have some subalgebra of the continuous functions on X. Then F is dense in the L infinity norm, so which means that F can approximate any continuous function on X with arbitrary good accuracy if and only if F separates points. Means that if I give you two different points in X, then there always exists at least one function in the function class F, such that F has different output on X and X prime. So the Stone-Weierstrass theorem tells us that as long as we have enough separation power, so we will have enough approximation power. So if we can separate all different points, then we can approximate any continuous functions. So, and this theorem tells us, okay, the separation power of graph neural network is equivalent to the separation power of WL test. So it cannot, so graph neural network by the Stone-Weierstrass theorem cannot approximate any continuous function on graphs. But sometimes we can also study. So even if it cannot approximate any continuous function, we find that it can approximate some special function related with LPs and MILPs. So here comes the third section, which is...
Sorry, can I ask a quick question?
Yeah, please.
Yeah, I have a question about the separation power you just mentioned. So, could you go back to the previous, maybe, yeah, that one.
Yeah.
So, I think it's true that these two graphs are like cannot be distinguished by the MPGNs, but I wonder, like, because although these two graphs are isomorphic, I think the corresponding optimization problem is also like equivalent, not like equivalent, right? Because actually you do not consider any no features or edge features here. So actually here the underlying optimization problem are also equivalent. So I wonder if there's an example of two graphs that contains like the no feature such that the optimization problem are actually different, but the MPN cannot distinguish.
Yeah, that's a very good question. I will give you the example later. So,
okay.
Yeah,
thank you.
So that's a very good question. It's essentially a key question in our papers. So here I will give you a first example. It is some examples of LPs, because that for LP we don't have integer constraint. So let's take a look at these two examples in the second column. So these two examples corresponds to the two graphs in the first column, and they are not isomorphic. The two graphs are not isomorphic. And we find that even if they are not isomorphic, they will have the same properties. So for example, the first graph, the first province is infeasible, and the second problem is also infeasible. So even if they are different, but they have the same optimization properties. And for the two graphs, for the two problems in the third columns, so they also correspond to the two graphs in the first columns. And we can say that the graphs are not isomorphic, but even if they are not isomorphic, these two problems will have some same optimization problems, some same optimization properties. For example, they are both let's see, they are both feasible, right? They are both feasible, and the optimal solutions and the optimal objective values are the same. So for both problems, the optimal objective value are two, and the optimal solution with the smallest L2 norm are also the same. So the answer is that the observation is that for LPs without integer solution, also without integer constraints, that for LP problems without integer constraints, even if the problems are different, they will share some same properties. And so this is not an example for your question, because you are asking whether we have some examples that their properties are different. So the short answer is that for LPs, we don't have such examples. And for MILPs with integer constraint, we will have such an example, which I will show you later. So let me summarize the observation here as a theorem. So if I have two LP instances, G and G hat, so if they cannot be distinguished by MP GNNs or WL test, they even if they are different or even if they are not isomorphic, they must share some common properties. So more specifically, they must have the same feasibility, they must have the same optimal objective value, and they must have the same optimal solution up to a permutation. And based on this theorem, so we can say that GNNs will have enough separating power. The GNNs, if we have two instances, and if they cannot be separated by GNNs, then they must have the same properties. So based on this theorem and the Stonewall-Sorare theorem, we can prove such a approximation theory. So for any probability measure P, and for any epsilon, so there always exists a GNN that such that the GNN can predict the feasibility of the problems with probability at least 1 minus epsilon, which means that the error or the loss is at most epsilon. And we also have similar results for the objective value and for the optimal solution, which means that, okay, for LPs without integer solution, GNNs can approximate the feasibility mapping and the optimal objective value and the optimal solution with absolutely good accuracy. Now I'm going to show you some numerical results for using GNNs to solve LPs. So we can see that also we randomly generate some data set for LPs, and we can see that if we use larger GNNs, or if we have more parameters in the GNNs, then the error or the training error can decrease to 0. Means that, okay, GNNs can perfectly fit the properties of LPs. And we also have some results on the generalization. It's very intuitive. If we have larger training sample, or if we have larger training sets, then the error on the test set will decay will also decay, and it will further decay to 0 if we further enlarge the training data set. Okay. Now I'm going to talk about the GNNs.
So may I ask a question?
Yeah, please.
Sorry for interrupting you. So I was wondering, like, but I roughly know the answer, but I just want to confirm. So we know, like, even for MLP, like, if we want to solve that, I think exactly, then the problem will be, I forget, like a NP complete or so it's not like we don't have like a polynomial algorithm, right? So I was wondering, like, why we may expect to have a GN here. So does it mean although the GN can represent the solver for the MLP for the LP here, so the number of parameters in GN will be goes to, let's say, exponentially with respect to M and N,
that's a very good point. So in our theorem, we have no guarantee on the complexity of the GNNs. We can only show that there exists some GNNs. There's no guarantee on the complexity. So my understanding is that if we want to use GNN to solve LPs or MIPs, then the complexity will be exponentially in MNN.
I see. Yeah, okay. And another question is about, like, the empirical side. So I was wondering, have you tried to test the generalization capability of the trained GNN here?
Oh, so that's a generalization. So we have some results on the testing error.
Okay. I see. Let me see this. So okay, so basically the generalization, there is still like some non-trivial generalization gap essentially, right? So but the training part. Oh, so for example, like when you want to test the feasibility here, what do we mean by 0.4? So is that like the 0 will be the best, and 0.4 means the 4, yeah, will be 40%, 45% of the case we fail, or
yeah. For 45% we will fail, but in this case we have a very small training set, and the size of GNN is also not large. Right?
Oh, okay. I see. So if we increase that, okay, we can improve the performance.
Yeah.
Oh, okay. I see. Okay, got it. So actually, this is really, so you're using very, very small GNN. So because I'm also curious, like just this I think this noon I chat with maybe how you're or Eli about this. So I was wondering, do you envision that we can train a GNN that have reasonably good generalization capabilities such that it can replace the current LP solver?
My understanding is that currently we cannot replace LP solver. The GNN is used to help LP solver. So
okay.
We can select algorithm for LP solvers using GNNs.
Oh, really? Yeah. So maybe we can check that more later. But yeah, I'm just curious. Okay, but I saw the generalization here. Okay.
Yeah,
okay.
Great.
Thanks.
Yeah. Thanks for your question. So now I'm going to show you some results on GNNs for MILPs. And here I will give you an example that we have two problems. And they cannot be distinguished by GNN, but they will have totally different properties, totally different optimization problems. So the story is totally different from the LP case. The theorem is that we have one feasible MILP and one infeasible MILP, and they cannot be distinguished by GNNs or WL tests, but they have the totally different properties, right? So you can see that one of them is feasible and one of them is infeasible. So here is the construction. So let's consider these two problems. So for the first problem, it is feasible because if we set x1 as 1, then x2 must be 0, then x3 is 1, x4 is 0, x5 is 1, and x6 is 0. So we have a feasible solution 1, 0, 1, 0, 1, 0. And it satisfies all the constraints, and all xj's are integer. However, for the second problem, it is infeasible. So if x1 is 1, then x2 is 0, then x3 is 1, then x3 plus x1 is 2. It is not 1. So we don't have a feasible solution for the second problem. Then we draw the MILP graphs for the two problems. We can see the first problems and the second problems cannot be distinguished by graph neural networks because every blue node will have the same neighborhood information, and every red node will also have the same neighborhood information. So this is an example that we have two problems that they have totally different properties, but they cannot be distinguished by graph neural networks or by WL tests. So if we input these two problems into MP-GNNs, then the GNN will give us the same prediction, but however, their feasibilities are different. So we can only have 15% accuracy. So we need to so in the case that we have integer constraints, we need to have some approach to resolve the issue, to increase the sampling power of graph neural network. So one idea is to only consider a subset of MILPs. So if we take a look at this example, so why it results in the failure of GNNs, the reason is that it has so many vertex with the same colors or with the same features. So yeah, we have 6 vertex in this graph and 6 vertex in this graph. They are both blue and they cannot be distinguished by WL tests. So we define a concept called foldable MILP. A foldable MILP is defined as that if we apply WL test or if we apply graph neural network, we will arrive some stable color, and in which the different nodes, some different nodes will have the same color. And we prove that if we have a probability measure on the data set such that the probability of the foldable instance are 0, means that for every data set, for every data point in the data set, if we apply the WL test, we will arrive. We will have different colors for different nodes. If we have such a data set, then we can find an MIP-GNN that can perfectly or with high probability correctly predicts the feasibility of the MILP problems. And we have similar theorems for the optimal objective value and for the optimal solution. Okay. Another idea, the idea of foldability MILP is not perfect because there is the issue that foldability or symmetry. So which means that we have similar we have the same color for some different nodes. So the foldability is very common in real world MILPs. For example, if we consider the data set MILP, then we can test whether the instance in the data set is foldable or not, and we find around 1/3 of the instance in MILP is foldable, which means that okay, so we can only use GNN to solve around 2/3 of the problems in MILP. So, and there are some other approach to identify and break the symmetry and the foldability. So the first approach is that suppose that we have two variables x1 and x2, such as they are symmetric. Then we can add a constraint. So we require that x1 is greater than or equal to x2. Then with this constraint, x1 and x2 are no longer symmetric, but we do not break. So we do not change the feasibility, the optimal objective value, and we at least keeps one optimal solution. So we can add this constraint without changing the province, and we can break the symmetry between x1 and x2. Okay, this idea is also included in a sequence of previous papers where they apply this idea to accelerate some conventional MILP solvers. So the second approach is the so-called randomized graph neural networks, for which we will add a randomized feature. We add a random feature for each vertex of the input MILP graphs. So if we have a random feature, then with probability 1, so with probability 1, all the nodes will have the different features, and hence they will have the different colors. Let me formulate the idea here. So we have an MILP graph, which is G. Then we randomly generate some features omega. So omega has an entry for each node and for each constraint and for each variables, which means that we add a random feature for each variables and for each constraint. Then we construct a GNN with this random input. Then we will have some random output depending on the random feature omega. So the result is that for any probability measure on MILP problems, if we construct another, so if we add a random feature, so the random feature is uniformly on this sample space, and we consider the probability measure after adding this random sample or after adding this random feature. In this case, we can find a graph neural network such that it can predict the feasibility with very high accuracy, with arbitrary high accuracy. And similar results also holds for optimal objective value and for optimal solution. Let me show some numerical results. So if we consider unfoldable MILPs, then if we consider foldable MILPs and we use graph neural network without randomness, then we will have, okay, so then the training error cannot decrease, okay, cannot decrease, no matter how large the GNN is. However, if we use the foldable, or if we use unfoldable MILP, problem, and even if we don't have randomness, we can still achieve 0 error in the training process. If we have foldable MILP, but if we can add some random feature, then we can see that the training error can still decrease to 0. So that's the idea. Either we can have unfoldable MILPs, or we can add random features, then we can achieve perfect training error using graph neural network. So here are some results in the generalization. We can still see that if we have larger training samples, then the testing error will be decreasing. Okay, that's a theory for using MP GNNs to approximate the end-to-end solvers for LPs and MILPs. So, any question for this part?
Yeah, Zhang, I indeed have some question. So, can you go to the slide where you're talking about like there are two different type of approaches. Yeah, yeah. Let me think. So because I also know some result like in let's say GN like expressive power, like some literature on GN expressive power where people mention like adding random features we can like have, let's say, you kind of like a uniform layer approximation with high
Yes.
probability. So I here for this I have some one question. That is, of course we know that in practice this method may not be used. The reason is generalization could be an issue because of random feature there. So, but I for you, like in your case, I was wondering if we just add random features, do you think how can I say this? Do you think the model indeed learn the way to solve MILP? So basically learn this ground truth function to solve the MILP, or it's just an overfitting of those random features?
I think it's an overfitting. So because the random feature is not an intrinsic property of the underlying MLP problem, right? So we just artificially create some separation power. We artificially create some additional separation power for graph neural network. So
I see.
So I think it's just an overfitting.
I see. So because this is also related to the theorem you're going to show there. So so essentially your theorem here is still try to, if I although you didn't show the proof there, but my understanding is you try to say, okay, if the model leverage those random features, then we can approximate, we can make its output close to whether it's feasible or it's infeasible, basically 0 or 1 with arbitrary accuracy. Is this something like you let's say you did in your proof?
Yes, I think that's the intuition. Yeah, that's the question.
Yeah, because I'm thinking, we know that so if we just say, okay, yeah. So for this is actually always in my mind, because I think even we add some random features because of like the GNN still follow those like a message passing way to do things. And essentially it's more like how can I say, it's more like let's say some let's say polynomials, and then some multivariate polynomials, and then do nonlinearity, some multivariate polynomials, and then nonlinearities. I guess overall the function, no matter whether there is random features or not, this function cannot represent the solver, cannot like approximate the solver for MLP, and also maybe for some traditional like triangle counting problem. So I guess it cannot do that. Like but why we may have the result there here is just because so right now our proof just leverage those random features and try to show the output will close to the ground truth as much as possible. So this is my, I'm not sure whether I express my understanding like clearly, but I just say no matter whether there is a random feature, the GNN's operation will not approximate the ground truth because of the limited expressive power. But why we have this result here, because we are trying to leverage those randomness and do something let's say random features do something like not follow the ground truth function, but follow something different. Yeah,
Yes,
yeah, this is, I guess, yeah.
Yes,
Well,
I understand your understanding, and I think it is correct. So actually, I don't think adding random feature is an efficient approach.
okay.
So actually, in our numerical experiments, we see that if we want use graph neural network to learn some symmetric MILP problems with random features, then we said we need a super large graph neural network to fit the problem case.
I see. Got it. By the way, another question is for the first method you mentioned. Yeah. So for the first method you mentioned, this is really interesting because I don't think this is valid for let's say general graph learning functions, but maybe it's a very nice trick for MLP solver. So I was wondering, have you tried to show the expressive power or like the functional approximation capability by using the approach 1, or any empirical result there?
So there are some empirical results, but not using graph neural network. So they apply this idea in the conventional algorithm for MLP, and they can see a lot of accelerations.
Oh, okay.
Yeah.
So can you explain a little bit why this way can give us a lot of acceleration for the solver?
So
yeah.
The idea is that so if we want to apply so in the conventional algorithm, they will use the so-called branching and bound algorithm, right? And the complexity or the running time will depend on the size of the branching bound tree. And if we add this symmetry, if we add this inequality, then so consider the case that we don't have this constraint. The x1 and x2 are symmetric. Then we need to branch in on x1. Then we need to branch on x1, and then we also need to branch on. We also need to do the branching on x2. So we need to do the same thing twice, and the two subtrees are actually the same. So we are repeating the same thing for 2 times. Then so it's a waste of time.
Yeah. So does the observation, does the like practical acceleration is about like, for example, if I add one constraint there here, is that like just double the speed, or let's say much more than double, or less than double, or yeah, I don't know. Of course, if we have like a lot of if we can add a lot of like symmetries, if each of them can improve the speed by twice, like by 2 times, then we have like 2 to the power of a lot, like, so that will be a great acceleration. I'm just so thinking about like in practice, if we just add 1, do you know like what that will happen in practice? Yeah.
My understanding is that we can skip one subtree in the branch and bound tree. So
okay,
it's around 1. It's around 1/2.
Okay. Got it. Okay, thank you.
Yeah, you're welcome. So also I have one more comment. So for example, if we have six nodes with the same color, then we add some constraint to break the symmetry between the 6 nodes. Then we can. So my understanding is that it will save around 5/6 of the total running time. Yeah, but that may not be correct because I do not check the running time. I did not really check the running time. It's just from the theory.
I see. And actually, let me think about this. I for this actually, there's a very interesting thing to use GNN here. I'm not sure, like in the traditional, let's say conventional solver, how they check which variables are symmetric, or let's say which 2 variables are symmetric. Is there a, let's say, efficient algorithm, or only checking this is also hard? Or not? I don't want to say it's hard. It's also time consuming in practice.
It's time consuming. So the worst case, the worst case complexity is exponentially in MNN. But they do something similar to WRTS, and they can find the symmetry. They can find all the symmetry.
I see. Yeah, because I'm thinking about like I see. But I roughly get the idea. So I'm thinking about this part maybe accelerated by GNN. I think if we use like a GNN to go feed the original model into GNN, and then maybe run several iterations. That will be fast. That can be, let's say, purely parallelized. And then we check the node representations, and based on the node representation, let's say whether two nodes have a very sufficiently close representation. If they are, then we add a hard constraint there. Yeah, I'm not sure whether, but maybe that's not feasible, because we will also add some variables that are not symmetry. I don't know. Like yeah, but I'm thinking whether that could be used or not. Yeah.
Yes, I think that's useful. Actually, the idea you mentioned is very close to the idea in this sequence of papers.
Oh, really?
Yeah.
Really? Maybe GNN can be directly accelerate this. I don't know. Like maybe how you do want to check the most recent one? For example, the Hongini, let's say Honey's one, like in 2019. Yeah, so I don't know, like I don't know like how long time it will take, but if we can use like a WL first to check the subgroup of variables that are symmetric under WL test, then that part can be significantly accelerated by GNN essentially. Yeah. Yeah, GNN is much faster than the let's say use the CPU like to run WL test. Yeah,
I see.
Yeah,
actually, in their algorithm for computing the symmetric group, they need to run WL tests for I think for at most n times.
I see.
So one WL test is not enough to capture the whole symmetric group. It needs to run a lot of times.
I see. Then I think this is a point GNN can be used. I'm not sure whether that's yeah, but I got that. That's interesting.
Great.
Yeah, so I also have a question.
Yeah, please.
About the experiment result. So like, I wonder, of course, you said there's a test accuracy or test performance, test error, but I wonder, like, does this test data sort of in the same size of, like, giving the same size of MILP, and the range of these values are also very similar, or you also test for a different size of MILP and different size of this range for these values?
In our experiments, we use the same size and the same distribution.
Okay.
So for training and test, but I know I know there exists some other works that they train graph neural network on smaller data, on smaller size, and they test it on very large size. Yeah.
I see.
Yeah, some empirical work. So someone is doing that, I think.
Okay.
Yeah, great.
Thank you.
So now let me present the last section. So in the last section, we want to use graph neural network to approximate the branching strategy of MILPs, because in the first section, we have already know that graph neural network do not have enough sapling power to represent the feasibility or represent the solution directly, or as an end-to-end solvers, it does not have enough sapling power. So a natural follow-up question is that can we use graph neural network to assist the solvers, or to represent some part of the MILP solvers, not the whole solvers. So we find that graph neural network can represent the so-called branching strategy for MILPs. So now so to introduce the branching strategy, so I first need to briefly introduce the branch and bound algorithm. Let's consider this example. So we want to maximize something, and we have a linear constraint, and all the entries of Z are integers. So we first solve an LP relaxation of the problem. So we remove the integer constraint, and we solve an LP we solve the LP relaxation. Then we found that there are some fraction number in the solution. So this cannot be the optimal solution because 1/2 is not an integer. So we need to consider two subtrees. So in the first subtree, we set Z1 equal to 0, and in the second subtree, we set Z1 equal to 1. Then if we fix Z1 equal to 0, so if we have Z1 fixed at 0, then the problems will reduce to a sub-LP. So because Z1 is fixed, so we have fewer variables. Then we solve the sub-LP. Then we solve the LP relaxation of the sub-MLP problems, and we can find the fraction solution. Then we say, okay, Z6 is a fraction number, so we can consider two different cases. So Z6 equal to 0 and Z6 equal to 1. Right? And if Z6 equal to 0, then Z1 and Z6 are fixed. Then we find something, okay, then we find another solution in which Z3 is a fraction number. So Z3, then we can do the branching on Z3. So the first subtree is at Z3 equal to 0, and the second subtree is at Z3 equal to 1. And we construct a tree, okay, so-called branch and bound tree. So that tree is used in almost all conventional MILP solvers. And okay, so if we consider this node, we will find an integer solution. So if we fix Z1, Z3, Z6, and we solve the LP relaxation, we get, okay, the solution is already an integer solution. So we will find something. So we don't need to do the branching under this node. And similar for here, so even if the solution is not an integer solution, but the objective function value is worse than the objective value of an integer solution we find. So we also don't need to consider all the branchings under this node. So it can be deleted because okay, so even if we allow some fractions, the function value is still not good, so we can delete it. So if we explore all the tree, we will find an optimal solution for the original MILP problems. And we can imagine that the efficiency of the algorithm highly depends on which node we choose to branch. Right? So so in this example, so if we first branching this subtree, then we do this subtree, then we will already have a solution in hand. Then after we arrived at these two nodes, we can delete them. So we don't need to explore because they are worse than the solution we have in hand. So however, if we explore this subtree first, then we don't have this solution in hand. Then we have to explore all the subtrees under those nodes. So it's highly time consuming. From this observation, we can say, okay, so the efficiency of the algorithm highly depends on which nodes or the ordering of the nodes we use to do the branching. So there is a heuristic on the order on which ordering we should use. The idea is the so-called strong branching score. So suppose that we have an LP relaxation. So we have an LP. So we have a solution. We have an optimal solution to the LP relaxation. Then we define the LP score for each node or for each variable. So if xj is not an integer variable, the strong branching score for xj is just 0. If xj is an integer variable, then the strong branching score of xj is defined in this way. So we already have the optimal objective value for the LP relaxation of the original problems. Then for any j, so we first replace the upper bound of uj. So we replace the upper bound of xj by the largest integer that is smaller than or equal to the jth entry in the optimal solution. So we have something. Then we replace the upper bound, or then we replace the lower bound of xj by the smallest integer that is larger than or equal to the jth entry in the optimal objective solution of the LP relaxation. Then we find then we find two optimal LP solutions or two optimal LP objective values. and we can define a SB score in this way. So in practice, the SB score is used to determine the order of the branching. Okay. So once we have the SB score, we can have some efficient, some empirically efficient way to order the branching, to order the branching. So the question is actually whether can we use the graph neural network to represent the strong branching score? And unfortunately, the answer is no for MP GNNs. So let's consider these two problems for these two problems, and we draw the two MILP graphs here. So we can see that these two problems are different, and the two MILP graphs are different. So they can but these two MILP graphs cannot be distinguished by WLTest or by message processing graph neural networks. So if we input these two problems into the message processing graph neural network, we will have the same prediction on the strong branching score. However, if we compute the strong branching score using the definition, we will see that the strong branching score for these two problems will be different. So this example tells us that MP GNNs do not have enough separation power to represent the strong branching scores. So the next question is that which types of neural network structure will have enough separation power to represent the strong branching score? So the answer is that the so-called second order folklore graph neural network will have the enough separation power. So the second order folklore graph neural network, so or in short, it is 2 FGNs, is defined in this way. So we assign the features for all the edges. So I is the i's constraint, and j is the j's variable. So we assign a feature on the on the edge connecting connecting vi and wj. We also assign a feature on the edge connecting wj1 and wj2. Then we do similar things as in the message passing layer. So we use local updates and message passing for features on the edge. Then we update the features on the edge iteratively. Then we finally output some vector, or we output some y, whose j's coordinates is the output on the j's nodes in W. So we define similar way, but the neighbors are defined with respect to some triangles. In one triangle, the two edges in one triangle will be regarded as the neighbors to each other. So if we have the two graph neural network defined, or two F graph neural network defined in this way, we can have a universal approximation theorem for the strong branching score. So the theorem is that for any probability distribution over the MILP data set or over the MILP instance, and for any given epsilon delta greater than 0, we can always find two FGNNs that can approximate the strong branching score very well, such that the probability that the distance, such as the probability that the error is smaller than or equal to delta is at least 1 minus epsilon. So let me explain the intuition behind this theorem. So as I mentioned before, the color updating rule of the 2WL test or 2FWL test or the 2FGN is based on monitoring the triangles, because the neighbors are defined using triangles, and the classical WL test is using the edge. So if we want to compute the j's entry in the strong branching score, what we did is that we fixed the lower bound. So we fix some j, and we change the lower bound and the upper bound, and we solve two LP problems. So if we fix the node j, and we run the 2FWL test, which means that one node of the triangle is fixed. So the triangle is determined by the other two nodes, which means that the triangle is determined by the other edge connecting those two nodes, one in V and one in W. So this is essentially the classical WL test. So this reduces to the classical WL test, And we have already known in our previous results that the classical WLTS or the classical message passing the classical message passing GNNs can solve LP problems. So after we fix Xj, so the problems would the WLTS will reduce to the classical WLTS, and we only need to solve 2 LP problems, and we know that the WLTS will have enough separating power for LP problems. So after fixing J, so we still have enough separating power to solve the LP problem, so we can compute the strong branch score. That's the intuition behind the theory. Now let's show some numerical results. So this is a very preliminary numerical results. So our data set has only 2 instances, so the first problem and the second problem. Two very small size two very small size MILP problems. And even on this very small data set, we still so even on this very small data set, we can see that the message passing graph neural network cannot achieve arbitrarily good accuracy. However, if we use 2 FGNs, we will see that when we train the neural network for long enough time, then the training error will decrease to 0. Okay, so that's the preliminary numerical results. And that's all I want to show you today. So let me do a quick summary. So basically, we study the separating power or the representation power of graph neural networks for LPs and MLPs. We see that the graph neural network will have some fundamental limitation in its separating power, and LPs do not suffer from this limitation, but MLPs do. So since LP do not suffer from this limitation, the message passing graph neural network can approximate LP properties universally. And after breaking the symmetry, the message passing graph neural network will approximate the properties of MLPs universally. And finally, we see that even if MLP graph neural network cannot approximate the properties of MLP problems, if we increase the complexity of the graph neural network, if we use 2 FGNs, we will have enough representation power to approximate the strong branching strategies of MLPs universally. That's all I want to present today. Thanks for listening.
Hi, Zhang. I have a very quick question.
Yeah, please.
Are you still doing some following experiment for the 2FGN method? I mean, some further numerical experiments.
That's the future work, so, but I do not currently working on that. That's a future plan.
Okay, thanks.
If you are interested, we can discuss about that further.
Zhang, do you have any intuition why I think the curve you show here, it seems that the training is really hard.
Yeah, training is really hard.
Right. So basically the model, it seems that like the optimization landscape has a very, let's say, quite flat, and only within a certain small region of the parameter space has a very deep, like a kind of let's say I want to say local or global let's say optimal point. So this is just something I'm interested in. So I was wondering what kind of do you still remember what kind of optimization, like a solver you are using there when training this GNN?
I think just the ADAM, right? Yeah.
Oh, but so I guess it's because you mentioned you just have one instance, right?
Two instances. So
2 instances.
Yeah, two.
Okay.
Instances.
Will they combine together to do the training, or will they fill into the same mini batch, or they will be iteration, like a iterate, different like
I think they will
iterate.
They will not iterate, so they will use in the same mini batch.
Yeah, my feeling is I guess when you do, I guess a better way at least to improve the optimization of the neural network is when you may want to do some like add some randomness during the training procedure. So this is my feeling. So I guess it's a or I don't know, like but I just guess when I saw the curve you show, it seemed that like it's really hard to train those models.
Yeah, it's very hard.
Yeah,
So
yeah.
I actually do not understand the difficulties quite a lot because the numerical experiment is not done by me.
Okay. Yeah. So.
Yeah, but Xiaohan told me that in the training process, so if we compute the strong branching score for these two instances explicitly, we will see that the score is the same for V1 to V8 in the first instance, and it will be the same for V1 to V6 for the second instance, but the score for V7 and V8 will be different. So he said that if we only consider these two instances, so at the beginning, so it's very hard to distinguish V7 from V6. And only when a lot of approaches are
okay to do that. So this is also given my feeling actually, but maybe it's you don't know that, but I guess Yinan knows. So my feeling is if we use, for example, like a 1D GN or like
what is 1D GN?
Yeah, essentially. So you can go to the previous slide, Zhang. So I think the next one. So I think the key insight here is we need the label for every node, every variable node, and then run GNN.
Yes.
So I think this is actually what we need, and actually in graph learning domain, and we have a bunch of several, let's say a lot of like literature on this kind of graph neural network, which recently people call it subgraph graph neural network, but I think previously very earlier one in my like a distance encoding paper, you can imagine I label each node as a distance that is distant from the others. Or later, people generalize this idea to, let's say, something called like a 1D GN. So IDGN. IDGN is more like, I label each node like a differently, like I label each node and then run GN and then aggregate the representation obtained by labeling each node. Together. So I guess that gives a way to is very similar as what you described here. The essentially where the expressive power, which is the more expressive power comes in to help you to handle like a strong branching problem.
That makes sense.
So I guess is maybe you even don't need to FWL. So you can even just use some expressive power given by IDGN or like one distance encoding or like or like recently people call it subgraph GN. So I guess that's enough. And actually I think some work has shown that those kind of line work, like those kind of models, are less expressive power than 2FWL. I think 2FWL is even stronger than that line, but I guess that line of work is already okay to solve your problem here.
Good idea. We can probably try that idea.
So I just think maybe. So and Okay, I don't have any other comments.
I have two questions. First one is that when you train the model, you try to test whether it is feasible for solving the RP problem or MIP problem, and also you need to find the optimal objective and also the solution. So when you try to train the model, what is used for the supervision and what is the prediction of the model? Do you need to train different models for different objectives, or whether it is feasible or not, and for things like this?
So first for the supervision, so we just use some classical solver like Groovy or Cplex to find whether it is feasible or to find the optimal solution as a label. And for your second question, so we use different model for feasibility and for optimal solution. We use one model for a single task.
Okay, so basically all these three metrics you train separate models to evaluate them on whether it is feasible. Okay.
Yeah. We use separate models in different tasks.
Okay, cool. Then the second question is when you try to find the optimal objective, it is just the error is MSE or MAE or something like this.
If I remember correctly, the error is MSE.
So did you ever consider using the do gap to evaluate the model?
We haven't tried that yet. That's should be a good direction to try.
Because like we know that the optimal value close, like the solver solve the problem and they get the results close to the optimal objective does not mean that is whether sensitive to parameter perturbation and whether it's have achieved zero do gap. This is not known.
Yes, but the issue is that in our experiments, the MILP instance or the LP instance are not large, so I don't. So I think the solvers can solve them perfectly. It's a super small instance.
Okay, yeah, that's actually my last question. Like, how large problem like you're solving right now, basically?
Okay, so if I remember correctly, for LP, it's around 50 variables.
Okay.
And for MIP, maybe 20 variables.
Okay.
And for the last experiment, 8 variables.
Okay, got it. Thanks.
I don't think we have any other questions from any other students. So by the way, Zhang, do you mind if we upload like your talk to the YouTube or
Of course you can upload. So I don't mind.
Okay, nice. Okay, then I think that's all. Like I think we have like a post lesson already. There's no questions. So again, Zhang, like thank you so much. Like yeah, so this is a very informative talk and we learn a lot. Yeah, so thank you thank you so much for coming here like to teach us. Yeah, great.
Thanks for your comments. I also learned a lot.
Yeah.